So this is chapter 16, Bronsted acid and bases. We will talk about acid and bases, their properties, the definition given by Bronsted and Lowry, the acid-base properties of water, pH scale, and the rest. So let's start with the acid and bases. So Bronsted acid is a substance that can donate a proton. And Bronsted base is a substance that can accept the proton. So in this context, the proton is represented by the H plus ion, because a hydrogen atom, which has one proton and one electron, and when hydrogen atom loses its electron, it becomes an H plus. And basically, H plus just has a proton, just one proton. So instead of H plus, we can just call it a proton. So if a substance donates a proton or H plus, we will call it the Bronsted acid. But if the substance can accept that H plus proton, we will call it the Bronsted base. Take a look at this reaction. So this reaction is HCl. We will call it the acid because what this acid will do in the water, in H2O, it can take this H plus and it can donate it to this H2O. So after this H2O takes H plus, then it becomes H3O plus. This is called the hydronium ion. H3O plus is called the hydronium ion. So what is left from this HCl after it donates H plus, just Cl minus. So we will put it the Cl minus. Another thing you have to pay attention. So HCl is the acid, but what is left of this acid after it donates H plus, we will call it a conjugate base. What basically the Cl minus can do in the water, Cl minus has the ability, should have the ability really to accept H plus and behave as a base. So NH3 is a base. We call it a base because according to the definition, it can accept a proton. So that's what it will do from H2O. So H2O can donate H plus to NH3 and take a look what happens to NH3. So NH3 and plus H plus, it will become NH4 plus. And the rest, what is left of H2O after it donates H plus, it's OH minus. So NH3 is a base, it accepts a proton, but after it accepts a proton and form an H4 plus, this substance we will call a conjugate acid, because what the substance can do, it can donate a proton and behave as an acid. So this will tell us, this table gives us a species, and it will give us the species and their pairs. It's like a pair of the acid and its conjugate base. So this is an acid. If you take out the H plus, so it's acid, you take out H plus, what is left? CH3COO minus, and that is conjugate base. H2O plus, take out H plus, you get OH minus, it's a conjugate base. NH3, if it can donate H plus, then its conjugate is NH2 minus. And the H2SO4, take out H plus, you get HSO4. So those are the conjugate acid and base pairs. But in this one, they're giving you the conjugate acid of some of the species. So if this will behave as a base, so as a base, it should accept H plus, and then H4 plus becomes its conjugate acid. They are now pairs of acid, conjugate acid, and base pairs. H2O, if it will accept H plus, then its conjugate acid will be H3O plus, OH minus the same. You add H plus to that, you get H2O. And for the urea, you add H plus and you get a conjugate acid of that. So this is, you make sure you understand how to separate Bronsted acid and base pairs. There's a difference between them in the H plus. So that's also they're telling you HCl is an acid because it loses a proton and it forms Cl minus as a conjugate base. H2O gains a proton from that HCl, and what is formed after that is its conjugate base. And the same scenario is for the base. This is a base because it can gain a proton and form its conjugate acid, NH4 plus. H2O here behaves as a proton donor, behaves as an acid. After it donates H plus, it will form OH minus or conjugate base. So make sure you solve the problems. You find their conjugate bases of HNO3. And of course, the conjugate base of this means this is acid. It loses H plus, and whatever is left, NO3 minus, will be a conjugate base of that. So this is an explanation given to you. They said to find a conjugate base of a species, just remove a proton from the formula. But if you want to find a conjugate acid, you add a proton to the formula. So practice with that, and so to master it. Now we will look at the acid-base properties of water. So water is called the amphoteric substance because what water can do, water can actually behave either as a Bronsted acid or a Bronsted base. It can donate and it can accept a proton. So that substance we call it amphoteric. So this is H2O liquid. This is a double-headed arrow. It will make H plus and OH minus. So this reaction is known as the autoionization of water. So the water, if you have two water molecules, you see you have two water molecules, they can ionize each other. One will behave as a acid or a proton donor. So and another will behave as a proton acceptor. So if this is an acid, so this water molecule will donate a proton to the base, and it will become OH minus, which is a conjugate base. And this the base water molecule will accept H plus and form a conjugate acid hydronium ion. So this is called the autoionization of water. So this is the reaction of the autoionization of water, and we can write down Kw. Kw, the water ionization constant. It's like an equilibrium constant. And we know for the equilibrium constant, what we write the concentration of the products raised to the power of their coefficient over the concentration of the reactant. But we also know, but if the substances are in a liquid or in a solid state, we do not include those substances into the expression of the equilibrium constant. So you can see the Kw equals to this expression, or instead of H3O plus, you can really write H plus. So this is exactly the same equation. At 25 degrees Celsius, the Kw value equals to 1.0 times 10 to the negative 14. In pure water at 25 degrees Celsius, the concentration of the hydronium ion equals to the concentration of OH minus ion, or they're both equal to 1.0 times 10 to the negative 7 molar. So the relative amount of the hydronium ion and OH minus ion determine if the solution will be neutral, any solution will be neutral, acidic, or basic. If the concentration of those hydronium ion and OH minus, if they are equal to each other, then the solution is neutral. If the hydronium ion concentration is greater than the hydroxide ion, concentration, then the solution should be acidic. When the hydronium ion concentration is less than the hydroxide ion concentration, then the solution is basic. So any substance you have, any solution you have, they both have the hydronium ion OH minus. They all have that, but their amount, their concentration will determine if that solution will be acidic, neutral, or basic. So you have to check those, which is greater. So that's another problem also is giving to you on, I put that on Blackboard for you. So you have to read this and understand this. Make sure you have the formula. But the formula will be provided to you on during the exam. I will make sure that you have formula and the periodic table given to you. The pH scale. So the pH scale is this is a formula of the pH. pH is a power of the hydrogen ion, power of the hydrogen ion. To calculate the pH, you have to take the negative logarithm of the concentration of H2O plus. That will be the pH, or the pH equals negative logarithm of H plus. When the concentration of the H2O plus equals to the concentration of OH minus, when the solution is neutral, and both the concentration equals to 10 to the negative 7 molar at 25 degrees Celsius in the pure water, then the pH of the pure water is equal to 7. So the pH of water is equals to 7. But the pH of water only equals to 7 at 25 degrees Celsius. It might be really different number, depends on the temperature. So at that temperature, if you have a pure water, their concentration are equal to 10 to the negative 7. If you take a negative log of 10 to the negative 7, you are getting 7. So, and remember also the solution where the concentration of those ions are equal to each other, the solution is neutral. If you have acidic solution, then the pH will be less than 7. When you have a concentration of hydronium ion greater than the concentration of OH minus. But if you have the concentration of hydronium ion less than the concentration of a hydroxide, then the pH will be greater than 7 and your solution will be basic solution. So acidic solution they have low pH, less than 7. Neutral solution has pH of 7, and the basic solution have a pH greater than 7. So they're giving you in this table the pH of some of the, they're giving you the benchmark pH value for some of the hydronium ion concentrations. So as you can see here, neutral is 7 at 25 degrees Celsius. Less than 7, your solution is acidic. Greater than 7, the solution is basic. In acidic solution, you have a bigger concentration of a hydronium ion, a lot of hydronium ion. And the basic solution, the concentration of hydronium ion is really small, getting smaller. This is a pH values of some common fluids. And if you have a pH, you can calculate the concentration of a hydronium ion. So that pH can be used to determine the concentration of hydronium ion. What you have to do, you have to take 10 and raise it to the minus pH value. Then you get the high concentration of hydronium ion. Again, this is a sample problems, how to determine the pH of a solution. So you just, if they're giving you hydronium ion concentration, so you will say pH equals negative logarithm of that hydronium ion concentration and find the pH. And this one tells you if you have a pH values giving to you, calculate the hydronium ion concentration. So you have to take 10 and raise to the minus of the pH to find the concentration of hydronium ions. pOH scale works the same as the pH scale, and the pOH is a negative logarithm of a concentration of OH minus. And if you have the pOH given to you, you can also find the concentration of the hydroxide ion. So this is another very important formula here, that pH plus pOH, they're equal to 14. So if you know the pH at 25 degrees Celsius, you always can find pOH. Or if you have a pOH, you always can find pH by looking at this formula. So they're also giving you the similar table, but only here you have a concentration of OH minus. When the concentration of OH minus is very big, your solution is basic. When the concentration of OH minus is small, your solution is acidic. Similar problems, same work.